So we've already studied the attractive force between two masses, known as the law of universal gravitation. That's what we did yesterday. That was the assignment that we were working on yesterday. But how can we explain this idea that two masses exert a force on each other but are not in physical contact? Okay, so when I think about me falling to the ground, we think of Earth is pulling, or has a force pulling me toward it, okay? But also, I am a mass, I am an object. The Earth is also, I'm also pulling the Earth up toward me. But we just watched on the Magic School Bus that a bigger mass will have more attraction. So between me and the Earth, which one is obviously much bigger? Earth.
Favorite question?
Pardon me? So the Earth is obviously much bigger than me. So its gravitational field strength is huge compared to the gravitational field strength I would exert on Earth. It's like pretty much nothing. Okay? So yeah, you could add that to your fat jokes or something. I don't know. Okay? But no, don't make fat jokes. Those are mean. Okay? Nobody makes fat jokes. Not here. All right. So, but out in space, what if two planets are similar in mass? Which one gets pulled toward the other? Rock, paper, scissors. No, we can calculate.
Oh.
Yeah, we can calculate it. So this is what astrophysicists will work with a lot. They apply these laws to planetary movement and how planets interact with each other. Whoa, and then we're going to do orbits after this, and then we're really going to get it. Maybe I should wear my planet dress again. Okay, moving on. All right. So planets and masses are actually attracting each other, but they don't have to come in contact with each other to be attracted. The idea of fields was created to describe why a force can be exerted without any physical contact. So it's saying like a field of energy is being exerted kind of thing. Fields are described as an action at a distance. Therefore, gravitational forces are due to gravitational fields. Okay? Every mass will create its own gravitational field, even if it is very small. So some of them are going to be so small that it's even pretty much negligible as to how much it is. Also, I forgot to note, can you all look in the back of your physics textbook and see if your physics textbook says Evan in the back of it?
Why do you not look again?
Just look. Whose? Okay, so that's Evan, and this is probably yours.
So Matt lost his card.
How did you get my book, Evan? You have my book.
Yeah, this one was left stranded.
So Hayden stole off. I didn't use mine.
Hayden, it's not nice to steal. Okay, so.
It's fault, though.
Yeah,
It's
we're
crafty like that.
Okay, so take out your formula sheets. Okay, and you should find these two formulas. Please identify those two formulas. What is on here, or on your notes, that's not specified on your formula sheet? There's one thing. There's something specific on here that's not on your formula sheet. M2 and M1. So what we're going to specify here, and you can write it on your formula sheet, for G is equal to FG go over M1. You can write M1 on your formula sheet. And for the formula that's right above it, you can write G is equal to big G times M2 over R squared. And I'll explain why next. So here, as I said before, we are going to call G gravitational field strength. Previously, we've referred to this as acceleration due to gravity. This is a synonymous meaning it's the same thing. We're just being more specific and talking about it as field strength, that a mass has that field strength. This can be measured in newtons per kilogram or meters per second squared. Either is okay. Either one is okay. Both are correct. So if you write your answer in newtons per kilogram and the answer in bold on your worksheets says meters per second squared, that's okay. Either one is correct, whichever one you choose.
They mean the same thing.
They mean the same thing. Because when we work through, because if you look at your Fg equals m times g, if we solve for g, okay, this is newtons. So newtons per mass is per kilogram. We know that G is measured in meters per second squared. So the units are the same. We classify newtons per kilogram as meters per second squared because a newton is a kilogram per meter second, I'm pretty sure. It's because a newton breaks down into kilograms and meters per second. Okay? So either unit is fine. Fg is the force of gravity, or the attractive force between two masses. M1 is the mass of the object inside an existing field. And we'll draw this in a second. And M2 is the mass creating the field. So M2 would be the bigger one. It's creating a field. R is the distance from the center of the object to the point in space. And our big G is our universal constant. So now let's just draw our M's, our M2 and our M1 to kind of conceptualize this. So say I have a big planet. Okay? I'm going to say this is M2, which up there is the object creating a field. A G field, I'll say. So M2 is my object creating a G field. Now let's say I have just a spaceship kind of floating in space out here. That's M1. It's inside this gravitational field. Now, we know that both actually have a gravitational field, but if it's like a planet and a spaceship, which one is obviously way bigger? The planet, okay? So we can draw in arrows pointing towards M2 because it's like there is a force pulling objects toward it. So this M1, this is a mass inside the G existing field, or the existing G field. Okay, so then also, we can also think about, say we have our planet again. So this is, again, is M2. And I have my field is pulling it all in. And the question just says, where in space is the gravitational field such and such? So you would just say, okay, well, this is just a point. There's not maybe a specific object there, but that's just a point. So this is used to calculate field strength at a distance from mass producing field. Now, depending on what you're given in your question, generally if you're looking at just M2, at M1, just looking at that mass inside the existing field, you'll use your G is equal to Fg over M1. So where M1 is specifically the mass inside the existing field. So that's not a formula that's foreign to us, right? This is the same thing as our Fg equals M times G. It's just rearranged. Okay? So this is one that we're familiar with. The only thing that's changed is that you need to think about just the concept of a gravitational field. That you are finding the gravitational field strength of that is exerted on that specific mass. Okay? This mass specifically. So you just... But these questions, you need to read them carefully. And sometimes I find drawing a picture will help. Okay? Next, if you're asked, like, if you're given just a point and you're trying to find out the field strength exerted by M2, you'll generally use little g equals big G times M2 over R squared. Both G's are figuring out the same thing, okay? It is the gravitational field exerted on M1 or basically like emitted or given by M2. Now, depending on what you're given, if you're given both masses to figure out Fg sometimes, you might need to still use this formula. So again, we'll do some examples, but you'll need to read your questions carefully. Sometimes you might have to use two formulas, sometimes you'll need one, sometimes, yeah. So